Hi, this is Lecture 7a, Part 2 for ECE 361, Probability for Engineers, Fall 2016. In this second part of Lecture 7a, we're going to cover the first part of material in Section 3.6, the continuous version of Bayes' rule. Let's recall what we discussed about Bayes' rule back when we discussed the notion of events. The basic idea was that we often have the phenomenon where there's a state of interest which we'll think of as a cause. And so we can think of there being, as in this setting, one of n possible causes. And then we observe something that is the effect of the cause. So the underlying cause in the laboratory may be controllable, and we know the probability of the effect given the controlled cause. In the language that we'll use below, probability of B given AI, where AI is cause I and B is the effect or observation. However, once we have used, say, our medical test in practice, we're no longer in the laboratory setting, and instead of controlling what the cause is and looking at the distribution on the observations or the effects, we now have this setting where the unknown cause, where the cause is itself unknown, and instead what we have access to is the observation, and we want to infer the cause. That is, we want to know the probability of AI given B, the probability of cause I given observation B. Okay, so with that as a high-level overview, let's go through this slide. So we think of event B as the effect, and we think this is what is observable. We will know whether the random outcome is in B or B complement. And we're interested in ascertaining the cause, which is not directly observable, represented by the partition A1 through AN. So in the classic setting, B is the outcome of a medical test, and the cause is, say, in the simplest case, A or A complement, the person does or does not have the disease, which the medical test is seeking to assess. So given that the test has come out a certain way, the natural question of greatest interest to the patient and the doctor is the probability of the cause, the disease, being there given the outcome of the test. So that's what this second bullet says. We're interested in the probabilities of each possible cause given the effect, that is the probability of cause AI given observation B. But our model tells us only the probability of the effect given the cause. That is, if we knew what the cause was, our laboratory test would tell us the probabilities of each possible measurement. So Bayes' rule allows us to flip things around. In particular, it allows us to obtain each of the probabilities of causes given an effect using the probabilities of the effect given the cause and the distributions of the different causes, the marginal distributions. All right, in particular, Bayes' rule says nothing more than the definition of conditional probability. The probability of cause A sub I given effect B is equal to the probability of B given AI times the probability of AI over probability of B. This is nothing more than the definition of conditional probability. And then the denominator is often expanded using the total probability theorem. Here, probability of B is expanded by conditioning on all possible values of A from j equals 1 to n. So that was Bayes' rule, and we covered that several weeks ago now, early on in the class. Now what we're going to do is derive a version of Bayes' rule for continuous random variables. So now we'll think of the random variable x as the unobserved phenomenon, that is the cause, and it's going to have some probability density function, little f sub x. Random variable y we'll think of as our observation, and it's going to have some probability density function f sub y, and importantly, a conditional distribution of y given x. And again, we think of this as analogous to measurements that might be made in a controlled laboratory setting. If we can control what the unobserved phenomenon would in fact be, we could measure the distribution on the observations. But now, outside of the laboratory, our objective is to infer x given y. That is, we've applied the test, we have an observation y, and we want to use it to assess the distribution on the unobserved phenomenon x. So Bayes' rule in this context gives exactly the analogous concept. The probability density function of x given y is equal to the following product and ratio. It's in the numerator, the probability of x, the probability density of x times the conditional probability density of y given x all over the probability density at y. And we can use the total probability theorem in its continuous form to condition on the value of x. We integrate over all possible values of x going indexed by t here, going from negative infinity to positive infinity, looking at probability density at y given x times probability density of x. So that's the continuous version of Bayes' rule, and we'll see how to apply it. All right, so let's do an example. The idea here is that what we're going to observe is a light bulb lifetime, y. And we suppose that the lifetime, y, is a function of the quality of the light bulb. And we think of that quality as the parameter in the exponential distribution governing the lifetime of the light bulb. So again, we're dealing with light bulbs that are assumed to be exponentially distributed with some parameter lambda. So again, recall the exponential distribution with parameter lambda has an expected value that's 1 over lambda. So a high value of lambda is going to correspond to a short average lifetime. A low value of lambda is going to correspond to a higher average lifetime. So what we're going to assume in this setting is that due to some quality control problems at the factory where the light bulbs are produced, that lambda, the control parameter, or the quality parameter of the light bulb, is itself a random variable. Namely, in particular, capital lambda is random and is uniformly distributed between 1 and 1.5. So again, remember that smaller values of lambda correspond to lifetimes that are larger, and larger values of lambda correspond to lifetimes that are shorter. So given lambda, given knowledge of the quality of the lifetime, quality parameter of the light bulb manufacturing process, we know the distribution of y. That is, it's easy for us to understand f of y given lambda is an exponential distribution. What we want to know instead is we measure a light bulb's lifetime and we want to infer what can be guessed about the quality control that gave rise to that light bulb. In other words, we're asking what is the most likely value for the parameter lambda given the observation of the light bulb lifetime that we saw. So our distribution on quality control is the uniform distribution as set up here. And of course, the constant 2 comes from the fact that the width of the support interval from 1 to 3/2 is 1/2, and therefore the value of the probability density function is 1 over that support length, or 2, for all possible values lambda between 1 and 3.3/2. So now what we're doing here is we're applying Bayes' rule. We're asking for what is the probability density of the quality control parameter lambda given the light bulb lifetime y, and what we're going to use instead of in order to get access to this, we're going to use the density of lambda, which is the uniform distribution, and the conditional distribution of the lifetime given the parameter lambda, which is the exponential distribution. So we plug in the 2 for the uniform and the lambda e to the minus lambda y for the exponential distribution. And down here we're integrating over all possible values of lambda going from 1 to 3/2. And we plug in the conditional distribution and the uniform distribution. And we get this following expression here, which is a function of lambda and y. So here's, on the next couple slides, I have some plots. On this plot, this is the conditional distribution of the light bulb lifetime given knowledge of the quality control parameter lambda. In particular, I have 3 curves here, one for 3 different values of lambda. So the blue curve corresponds to lambda equals 1, its smallest value. The yellow curve corresponds to lambda equals 5/4, the middle value, and the green curve is for lambda equals, 3/2. Okay, so this is the conditional distribution of y given lambda. This is the exponential distribution with 3 different rate parameters. And you see that when lambda is small, there's a higher probability of a longer lifetime. when lambda is large, there's a higher probability of a shorter lifetime. This is the marginal distribution for y obtained by the total probability theorem, integrating over all possible values of lambda, weighting them by their suitable probabilities. And this is the distribution that results. This is to be thought of as a mixture of all possible exponential distributions, each one weighted by the corresponding uniform probability. Finally, this is the distribution on the value of lambda given the observation duration of the light bulb lifetime. It's often called the posterior distribution. So here, the x-axis here is the lambda axis going from 1 to 1.5. And again, we have three curves corresponding to three different values of y. The blue curve corresponds to observing a lifetime with duration 1/10. The yellow curve corresponds to observing a light bulb with lifetime 1. And the green curve corresponds to observing a light bulb with lifetime 10. So we see that when we observe a very short lifetime, the probability density function on lambda is higher for higher values of lambda, recalling higher values of lambda correspond to shorter values of the mean lifetime. Similarly, when the observed lifetime is long, we see that the higher probability is on the smaller side of lambda, again because longer lifetimes corresponding to smaller values of lambda being more likely. Next, let's talk about inference about a discrete random variable. So in this setting, we're supposing that the unobserved phenomenon is binary. It's either present or it's absent. And we'll let A be the event that the phenomenon is present, and P of A the probability of its occurrence. Now we're given an observation. Say we call our observation the random variable y, and we suppose it takes value little y. And we're interested in understanding the probability that the phenomenon of interest has occurred given that our observation is little y. And for small enough delta, this event that random variable y is equal to little y is approximately the probability of A given that y is in some interval, y to y plus delta. And now by using Bayes' rule, probability of A given y in this interval, flipping things around, Bayes' rule tells us this is the probability of A times the probability that y is in that interval, y to y plus delta given A, all over the unconditional probability that y is in that interval, y to y plus delta. Now, this quantity here is the conditional density of y given A times the width of the interval, delta. And this denominator here is the unconditional distribution, unconditional density for y at little y times, again, the width of the interval, delta. You see the deltas are going to cancel. And so what you're left with then is a version of Bayes' rule suitable for this situation that we have here, where the underlying cause of interest is discrete, namely present or absent, and the observation is continuous as captured by the random variable y. In particular, the probability of the phenomenon of interest, given that we've observed little y, is equal to, by Bayes' rule, probability of A times the conditional PDF of y given A all over the marginal PDF for y. And now we're going to use the total probability theorem on the denominator. So in this setting, when A is dichotomous, meaning either A or A complement happens, then we replace the f sub y in the denominator by f sub y given A times probability of A plus f sub y given A complement times the probability of A complement. Okay, just total probability theorem. Now, if instead we were in a different setting where instead of the event of interest being dichotomous, either A or A complement occurring, if instead it was something where the event of interest was a discrete random variable, say capital N, then the probability that the random variable capital N takes value little n, given an observation capital Y being little y, is going to give you a version of Bayes' rule like this, and see if you can derive this given what we've said just now about the dichotomous situation. In particular, here we have the probability mass function for the random variable n evaluated at little n times the conditional density of the random variable y, given knowledge that the random variable capital N equals ln, and here we've again used the total probability theorem to get the marginal, the probability for y, or probability density for y, expressed as a weighted sum of the conditional densities for y given n, weighted by the probability of n. Let's do an example. This is a very important example in signal processing. So in this example, which is about signal detection, there's a binary signal, and it's either +1 or -1 that's going to be transmitted in each time slot, say. And the +1s and -1s don't occur with equal probability. So if you look at a long stretch of signals, p is the fraction of signals that take value +1, and 1 minus p is the fraction of signals that take value -1. So little p here is a fixed and known parameter, p, giving the relative fraction of signals that take +1. Okay, so little p is an important parameter for us. Now, the transmitter sends the signal, either +1 or -1, but it's corrupted over the channel by noise. So the observation, which is again y, is going to be the signal plus noise n. And now our noise is assumed to be normally distributed with mean 0 and variance 1. And also, as is common, we're going to assume that the noise is independent of the signal. So in particular, conditioned on the value of the signal, we have that the distribution of the observation given the signal is normal with mean equal to the signal value and variance 1. And the question is, if you observe a certain value little y, estimate the probability, or find the probability rather, that s equals +1 was sent. And of course, whatever that probability is, 1 minus that probability is the probability that -1 was sent. Okay, so let's take a more graphical view of this. So what we're thinking of here is that this is the y-axis, all right? And I have two vertical grid lines here at +1 and -1. And this blue curve is the distribution of y given that s equals -1 was sent. The yellow curve is the distribution of y given that s equals +1 was sent. And so you might think that the right answer is to simply do what might be most intuitive, which is, well, you look at these curves, blue and yellow, and you see whichever one is higher for the given value of y, and you guess that that curve was the one that was generated. In particular, we see that for y greater than 0, the yellow curve is above the blue curve, and therefore you might be inclined to guess that whenever you have a positive value of y, you should guess that the yellow curve was sent. And likewise, if y was less than 0, you see that the blue curve is always above the yellow curve. You might be inclined to think that you should guess that -1 was sent. The problem with this logic is that it ignores the additional knowledge we have access to, which is that we know that the prior probability that +1 was sent is p, and the prior probability that -1 was sent is 1 minus p. That's what this means down here. This obvious decision rule to guess s equals -1 if y is less than 0, or s equals +1 if y is greater than 0, ignores the knowledge of p, the transmission probabilities. So not surprising, we're going to use Bayes' rule. Okay, so we want to know the probability that a +1 is sent as a function of, or given, knowledge of our observation being little y. By Bayes' rule, this is equal to the following fraction. In the numerator, we have the prior probability of a +1 times the conditional probability density for y given s equals +1. And in the denominator, we have the prior probability of a +1 times the conditional density given +1 plus probability of a -1 times the conditional density of y given s equals -1. And now we can substitute in because we know all these distributions. We know the probability of s equals plus 1 is p. That's how the p here, and the 1 minus p here come about. And moreover, we know the conditional distribution of y given the signal. In particular, given the signal is plus 1, the density is the normal distribution with unit variance and the mean at plus 1. And that's the same expression down here. And now over here, which is the conditional probability density for y given s equals -1, we see we have y minus -1. So some of these terms will cancel out, and you end up with a simpler expression, namely p times e to the y over p times e to the y plus 1 minus p e to the minus y. So, as we said before, whatever this expression is, 1 minus this expression is going to equal the probability that s equals -1, given that y equals little y. And so now the decision rule should be compute probability that s equals plus 1 given y, and compute probability s equals -1 given y. Whichever one is larger is the one you guess. It's called maximum likelihood. Now, so the decision threshold is where the boundary occurs is when y is such that this probability is equal to 1/2, because if probability that s equals plus 1 given y equals little y equals 1/2, then of course probability s equals -1 given y equals little y equals 1/2 as well. So if I solve this equation, which is given by here, equal to 1/2, and solve for y, I'm going to get y as a function of p, given by 1/2 log 1 over p minus 1. And the way to think of y of p is, if I tell you p, the probability or fraction of symbols that are plus 1 in the transmission sequence, then this is the critical value for y, such that if you observe a y above y of p, you guess plus 1, and if you observe a y less than y of p, you guess -1. So here are some distributions on the probability that s equals plus 1 as a function of y for 3 different values of p. So the y-axis, or the x-axis rather, is y, and the curves here are the conditional distribution of the probability of s equals plus 1 as a given knowledge that the observation is little y, for p equals 1/4 here in blue, 1/2 in yellow, and 3/4 here in green. And I've drawn a horizontal grid line at 1/2, and you see that the vertical grid lines are where those lines intersect that 1/2 grid line. In particular, the blue curve corresponding to p equals 1/4 intersects 1/2 at this value just above 1. And so the interpretation is going to be then that if we know p equals 1/4, then we're going to guess that s equals plus 1 for any y above 1, roughly, and s equals -1 for any y less than 1. If, on the other hand, we knew p equals 3/4, which corresponds to the green curve, then our threshold is roughly just around -1. And now we're going to guess s equals plus 1 for any y greater than -1, and we're going to guess s equals -1 for any y less than -1. So here's this function y of p, the 1/2 log 1 over p minus 1 function. And again, p here is going from 0 to 1. So if I had p equal to 3/4, as we said before, then we see roughly that line is going to intersect at around -1. And so we see what this tells us is that if you choose p equal to, say, 3/4, you look up y of p roughly at -1. And if y is above y of p, then you guess plus 1. If y is below y of p, you guess -1. And that's the end of this topic and of this lecture. Thank you.